So what we need to start with is determination of stability. So if you remember, we define stability that's basically starting from some initial condition, the system, the outputs of the system will stay bounded and converge to typically a fixed number. Okay, so now the question here is, if I give you the characteristic polynomial of a transfer function, which means the polynomial of the denominator, where the constant term is not equal to 0, an. So the format for the polynomial is like this: a naught s to the n plus a1 s to the n minus 1 all the way to an. All of the coefficients are real numbers. The constant term is not 0, which means s of 0 is not a root. Also, the important thing, or now first I give you this and then I ask, okay, just by looking at this polynomial, could you tell me whether the system is stable or not? Which means basically whether all the roots, which we call them the poles of the system, whether they're all on the left side of the imaginary axis, or there is one, at least one, on the imaginary or to the right side. So the Ruth Hurwitz criterion said, if these are all real numbers, the constant term is not 0. Also, he mentions that if none of these coefficients, a0 to an, if none of them is 0 or negative, if there is one of them that is 0, including an, if one of them is 0 or negative in the presence of other positive coefficients, then there is a root, or there are roots that have what? Positive real parts, which means the system is unstable, or they are pure imaginary, which means the system is marginally stable. Okay? So it says if such condition exists, then you don't need to go any further. Just observe that and see if one of the coefficients is negative, if the rest of them are positive, of course, or is 0. That means you have something that is imaginary or with positive real part. But if all of them are positive, nothing is 0, now how can I tell whether the system has any root to the right side or on the imaginary axis or not? Okay, so let me first go through a couple of examples first, and then we come back and talk about this criterion. So let's say the polynomial that I have is of order, whatever you want to call it, order 5. So we have s to the 5, and then let's say 2s to the 4, and then 1s cubed, and then let's say 4s plus, so let's make sure, s to the 5, 4, 3, 2, 1, and then let's say a constant. Okay, so it's a fifth order polynomial with 6 coefficients. And then I use the command roots. You know, roots will give you what? The roots of a polynomial for which you are specifying the coefficients of. So if you look here, 3 of the coefficients have a negative real part, so they are good, but 2 of them don't. These 2 guys have a positive real part. So this system is what? Not stable, okay? Because 2 of the poles have positive real parts. So the response corresponding to this, because they have also imaginary component, is going to be an exponential. It's going to be a harmonic, a sine or cosine, but with magnitude that is, with amplitude that is increasing and ultimately go unbounded. This is just pure exponential decay, and these two are harmonics with exponential decay. But these two are harmonics with exponential growth of amplitude. So the system goes unstable. Now, if let's reduce the order to order 5, still you see, to 4 actually, still you see the system is possible for it to have positive roots. I just want to look at a scenario that, there we go. So this one, which is basically a third order, so it's s cubed plus 2s squared plus 1s plus 1. This guy has what? All three of the roots having negative real parts. So this system is what? Stable. Okay, now if I change one of the coefficients from all positive to one negative, now look. You see? So because there is a negative in the presence of the rest of the positives, then there is what? There is at least one of them. Now when there are complex numbers, there are a couple of them, because you know complex numbers always appear as roots of a polynomial as conjugates. So if z is a root of a polynomial, then also z bar is. So here, two of the roots make system unstable. Because what? Because I have one root that is what? Negative in the presence of positives. Or I make what? One of the roots 0 instead of negative. And you see, again, I have what? I have roots with positive real parts. While here, I had everything positive, nothing was 0, and everything was good. But that's not always the case. I have other cases where what? Everything is positive, none is 0, none is negative, but still I have what? Positive roots. So for these cases where I cannot just simply look and say, hey, there is a negative, system is unstable. There is a 0, system is unstable. For these cases where I cannot use the first method, the first fast check, for these cases, this method is giving you a help. And this method will tell you whether the system has roots with positive real parts, and if it does, how many. Not only it tells you if it does, it tells you how many. And then before we go and even look at this method, you might wonder, why should I do that? What's the point? Why should I do such a thing when I simply can use the command roots in MATLAB? Why should I do all sorts of tests? Because you see, we form a table and then we look at that table. Why should I do that when I have the coefficients of this polynomial? I simply enter them in a numerical solver like roots, the command roots in MATLAB, and that will give me all the roots. And if any of them is having a positive real part, then system is unstable. If one of them is pure imaginary, then system is critically stable, and so on and so forth. When I have this simple, nice command that can tell me everything I need to know, what's the point of this? And I'll tell you why. One of the major advantages of this root method is not just really telling you whether the system is stable or not and how many roots with positive real part it has. One of the biggest advantages is this part. It gives you ranges for some parameters in the system, so that for those ranges of parameter the system is stable. Outside those ranges the system is not. So it gives you inequalities for some of the parameters in the system that you can change, you can tune. Okay, that's the big advantage of this method. Okay, the roots command cannot give you such a thing. Okay, when you do roots, it's a numerical solver. So if instead of 4 you plug in a k, it's not going to give you the roots based on k. Okay, so you might say, what is it based on k? It might or might not. So what are you talking about? I have no idea what you're talking about k. Okay, but this method is giving you inequalities. So the major advantage is again here, and we go through that. But first, we need to know how this method works. So one last time before we start. We have this polynomial in the denominator of a transfer function. All the coefficients are positive. Nothing is negative, nothing is zero, and the constant term is also not zero. Can we tell whether there is any root here to the right side or on the imaginary axis? And if there is, how many? Yes. The Ruth Hurwitz method says do this. It says first form a table that you can see here in red. Here I have added the original polynomial on the top for your reference. So he says the first row of the table are basically starting from the leading term, a0. Every other term you put the coefficient down here on what? On the first row until you get to the very end of it. So we start with a0, then go a2, a4, a6, all the way to the place that is like the last coefficient that you can reach. And if you see the subscripts here, the index of these parameters, they're all even numbers. For the next row, you start with the second term, and then again, every other term, you go forward until you get to the very end of it. So a1, a3, a5, a7, so the coefficients with an odd subscript, go forward and add them to the second row. Now, from the third row, start calculating the numbers. How? B1, this first element, is going to be, if you draw a 2 by 2 matrix between a0, a1, a2, and a3, then the determinant of this matrix with a negative sign is going to be what? a1, a2 minus a3, a0. You know, in determinant you multiply diagonals minus anti-diagonals. Here is the opposite. If you see here, you multiply the anti-diagonals positive, then minus the diagonals negative, and then divide it by this number right above B1, which is A1. For B2, you're not going to simply shift this 2 by 2 matrix 1 unit to the right. What you do is you basically make this guy a little bit longer. So you bring it like this, but you eliminate this column right above B2 because you used it already one time for B1. So this time you repeat the same thing, but between A0, A1, A4, and A5. So you say A1, A4 minus A0, A5, and again divided by A1. And then for B3, you do what? Again, you extend this. And since now you use the two columns of 2, 3, 4, 5, now you do it between A0, A1, and A6 and A7. In other words, in all of the B numbers, the first column is fixed. You always use the first column, and as you move forward in this row, use one of the columns, okay? So first and second for the first one, first and third for second one, first and fourth for third one, and so on. And you divide all of them, as you can see, by what? By A1. So the denominator for all of them is A1, and then you exactly repeat this process for what? For C1. So for C1, you do it between A1, B1, A3, B2, then A1, B1, A5, B3, A1, B1, A7, B4, and so on, and you form the C rows, then you form the D rows, and repeat until basically you get to S to the constant, S to the 0, or a constant. So here, the first row corresponds to S to the n, the highest power. The next row corresponds to S to the n minus 1, the next one S to the n minus 2, and so you keep going down until you get to what? S to the 0. And when you do that, then you will get like a pyramid, like a rectangle, an upright rectangle, with the first two rows being the longest row, and as you go down, you get smaller and smaller. When you get to S to the 0, you get a single number. Okay, you won't get a row, you just get a single number. And now, if you look at this table, the one column that has all numbers in it, everything exists for that column, is the first column. A0, A1, B1, C1, D1, all the way to whatever you want to call. So now the important is look at the first column. Okay, you look at the first column. So this method says if there is any change in the number of signs of coefficients, if there is any change in the sign of the coefficients, then there is definitely a root to the right side or on the imaginary axis. So definitely the system is unstable if what? If you see any change in the sign of the coefficients of this first column. So let's say if the first two numbers are positive, which we said we should consider positive, then the rest of the column also, all of these numbers, B1, C1, D1, all the way to the end, all of them should also be positive. If you have a change in the sign, so let's say B1 is negative. When you go from a positive A1 to a negative B1, there is one change in sign, and then when you go back from negative B1 to positive C1, that's another change in sign, so 2. Since there are 2 changes in the sign, it means there are 2 roots with the positive real parts. So as many number of changes in the sign that you see in the first column, it means those there is exactly equal to that number then the roots that have a positive real part. So let's talk about it by doing it instead of just me reading over the slide for you. So let's do it. So it says if the polynomial in the denominator is this guy, s to the 4, 2s squared, 3s, 2s cubed, 3s squared, 4s, and 5. Does this characteristic polynomial have any roots on the right side of the imaginary axis? So what we do is we form the table. We start with the highest power s to the 4, then we go s3, s squared, s to the 1, and s to the 0. So our table should have basically 5 rows. Now, for the first row, we start with the highest coefficient, with the leading coefficient, which in this case is 1. So I put 1. Then I jump, go to the third term, which is 3. And then I jump one more, and I go to what? 5. Okay? This 0 is just means find the root, so it's nothing here. So I found 1, 3, and 5 for s to the 4. Now for s cubed, I start with the second term, which is 2. Then I jump, go to 4. And now when I jump more, there is nothing. So that's it. These are what? These are the 2 rows of my table, Ruth Hurwitz table. Now I start calculating my third row. So for this element here, I consider this matrix. I multiply what? The anti-diagonals, so it is going to be 2 times 3 minus the diagonals 1 times 4, and then divided by the element right above it, which is 2. So if you calculate 6 minus 4, that's 2. 2 divided by 2 is what? 1. Okay, so I replace it for you here. This whole thing, it is going to be what? Is going to be 1. Now I want to come here. For this one, I need to use again the first column. The first column is constant, and now the third column. Now the problem with the third column is I don't have any number here. When you do not have a number, you artificially add a what? a 0. So whenever you do not have a number, you add a 0. In that case, you will get 2 times 5, 10, minus 1 times 0, which is 0. So 10 minus 0 is 10. And then again, you divide it by 2. So 10 divided by 2 is going to be what? 5. Okay? So that's how I go forward. Again, 2 times 5 minus 1 times 0 divided by what? Divided by 2. So I write it for you and then I clean it up. Okay, so I just want to make sure that I have something for you, for your record, that you can go back and watch. So this was 2 times 3 minus 1 times 4, and then the whole thing divided by 2. So this is 1, that is 5. Okay, so now let me clean it. Now, that's it. Now I come here. So when I come here, now I have to use what? This column and this column. So this number is going to be what? 1 times 4 minus 2 times 5 divided by 1, which is what? 4 minus 10 divided by 1, so it is going to be negative 6. Right? So it is going to be what? Negative 6. So let me write it. Again, when I want to go here, for here I have to use this column and then that column. But here I don't have a number. So again, I artificially add a what? 0, and of course you get 2 times 0 minus 1 times 0, so 0 minus 0, it's 0 divided by 1, you will get a what? You will get a 0, of course, because there is nothing there. And finally, we go to last column. For last column, you use negative 1 and 6, 5 and 0, so it is going to be negative 6 times 5 minus 1 times 0 divided by negative 6, which is going to be what? 5. Okay, so I write 5 down here. So my table is done. Now, all I care about is the first column. Do I see any change in the sign of the coefficients here? Yes. I see they were positive. Once I came from here to here, that is one change. I went from positive to negative, and when I came from here to here, again, it went back from negative to positive. So I have 2 sign changes, right, in the first column. Which means what? There are 2 poles or roots of denominator with what? With positive real parts. And so means the system is what, of course? Unstable. So clearly system is unstable. How many roots, how many poles do I have on the right side of imaginary axis? 2, because I have 2 sign changes in the first column. And we can always check it just by going back to MATLAB and using the roots command. 1, 2, 3, 4, 5 are the coefficients, right? So we just use that. 1, 2, 3, 4, and 5. And if you look at the 4 roots, 2 of them have what? Positive real parts. Okay? There we go. So that's how this method works. Again, you might say, why should I do all of that table? What's the point of doing all of that table if I can just come here and type in command roots and get all of the info that table is going to give me, I can directly watch it here. And you are right, that's a valid question, but that's not all that this method does. So before I go any further, there are two exceptional cases that we have to handle for this method. One is if there is number 0 in the first column, and second is if all of one row in the table is 0. So those are two exceptional cases that I have to tell you how to handle them. But before I go to exceptional cases, let's talk about the real application of this method. So the real application says I can give you inequalities, okay, and that's the main power. So let me show you. So this is the other problem I want to solve for you. It says this is my system, okay, there is no transfer function in the feedback, so h of s is 1, that is g of s. Okay, so this is g of s, h of s is equal to 1, there is no sensor or feedback transfer function. In this system, if you calculate C over R, the closed loop transfer function, based on what we learned, it is going to be g of s over 1 plus g of s times h of s. And since h is 1, it is going to be basically k over s times s squared plus s plus 1, the whole thing times s plus 2, and then divided by 1 plus the same thing times 1. And if I simplify, I will get k over, so here I have to multiply all this together and then add k to it. And to do that, I can use MATLAB, so I multiply s by s squared by s plus 2, so it is going to be s squared plus 2s, and then I multiply by this to find the resulting polynomial. So I use the conv command. So I say, what is conv of, for one of them was what? Was s squared, s, and 1, so 1, 1, 1. That's one of the polynomials. And the other one is what? Basically s times s plus 2, right? S times s plus 2, which is s squared plus 2s. So this is s squared, this is 2s, and there is no constant, so I plug in 0, and that's the result. Okay, this is constant, this is s squared, s cubed, s to the 4. So 1, 3, 3, 2, 0. 1, 3, 3, 2. So it is going to be like this. 1, 3, 3, 2, and then for 0, since you add this constant k to it, your constant in the denominator will be k. So this is your closed loop transfer function. And so your characteristic polynomial is this guy here. So now, what does the problem ask? The problem says, well, for what range of k the system is stable? So this k is a parameter that you can change. Okay, you can turn a knob or change this parameter, you can tune it. But not for every number of k that you plug into the system is stable. For some values of k is stable, for some k's it's not. How can I find it? And that's what this method gives you. So it says first find the characteristic polynomial that we did. Now form your table. So we have s to the 4, s cubed, s squared, s, and s to the 0. Form your table. put the coefficients down, so it is going to be 1, 3k. So k here is a parameter. Here it's going to be 3, 2, and nothing. And we learned that when we have nothing in the second row, we have to artificially add a what? Add a 0. Okay? So let me use a different color so that you know that's not from these coefficients we artificially added. Okay, now we come to here. It is going to be 3 times 3, 9, minus 2, which is what? 7, and then divided by 3. So it is going to be what? 7 over 3. Then I go to the first column and third column. So 3 times k, that's 3k, minus 1 times 0. Again, 3k. 3k divided by 3 is what? K. Then I come here. So it is going to be 2 times 7 over 3, so 14 over 3 minus 3k. So let me write it down. 14 over 3 minus 3k. Then the whole thing divided by what? 7 over 3. The next one, I don't have anything, okay, to go, because it is 7 over 3 and 3, and this is 0. Again, I have to add artificially a 0, and if I do so, then the result is simply going to be 0. And so now when I come here, I multiply these together, and then minus these two, and then divided by this, so the result is simply going to be k. So now I look at the first column. If I want this system to be stable, there should be no change in the sign, which means since the first 3 are positive, the rest of it should also be positive. Okay, so everything should be positive. So I get 2 inequalities. One, k is positive. The other one is 14 over 3 minus 3k divided by 7 over 3 should also be what? Positive. Now here the denominator is positive, so the numerator should be positive. And if you solve for it, k has to be less than what? 14 over 9. So you see, k has to be positive, yet what? Less than 14 over 9. So my condition is this. Only inside this range, the system is what? Stable if k that I put into the system is anything other than this range, the system goes what? Unstable. So this is the power of this method. It gives you stability conditions or inequalities for parameters that you have control over and you can change. Okay, so of course, yes, if you don't care about this and you just want to know whether there is positive or not, and all of the coefficients are just simple numbers, none of them is a parameter, then yes, you can just use the roots command. But that's the power of this method. Okay, so that's why we study this algorithm. Okay, now as I said, there are 2 scenarios that might happen, and they make the calculation of the table a little difficult, but we can handle it. Scenario 1. In the first column, 1 0 element appears. So when you want to calculate the rest of the numbers, you will face a division by 0. Okay, you will face a division by 0, and of course you cannot divide by 0. So how do you handle it? So let me tell you. And the solution is written here, but again, instead of me reading over that, I want to do it, and then I'll come back and we'll look at it again. So it says, if this is your characteristic polynomial, okay, again, we don't care about this part equals 0. We know we have to find the roots of it, so make this 0. So that's not a major thing for us. So we form a table, s cubed, s squared, s to the 1, and s to the 0. start with coefficients, so it is going to be 1 and 1, and then it is going to be 2 and 2. If I calculate this number, it is going to be 2 times 1 minus 2 times 1 divided by 2, so it's 0. Right off the bat, 0. Okay, this one, it doesn't exist because there is no third column, so this is just basically nothing. You can say that one is also 0, okay, because nothing exists in the third column to calculate that. So you can artificially say third column is 0, 0, and that will lead to what? To a 0 here. Okay, now when you want to come here and calculate this, now you use what? The first column and the second column above it, so it is going to be 0 times 2 minus 0 times 2 is 0, so the whole thing is 0, and then divided by 0, so you will get 0 divided by 0, which is basically ambiguous. There is no solution to that. We don't know how much it is. Okay, so that's not going to work. So what we do instead of 0, this is what we do. We consider a very, very small positive number instead of 0, and we call it epsilon. So epsilon is a very small number, yet positive. So epsilon is like what? A lot less than 1. It's very small, and yet what? Bigger than 0. And I replace that actual 0 with this artificial 0, which is not pure 0, but it's a very small number, 10 to the negative 16 or whatever. And you might say, where did you get 10 to the negative 16? That's epsilon of MATLAB, right? In MATLAB, if you type in epsilon, EPS, I guess. This is the smallest number that MATLAB can use for keeping the accuracy of your arithmetics. In other words, if you add or subtract numbers that are below this guy, they will be rounded to 0. Anything less than this in MATLAB is considered 0 because it has so many zeros that MATLAB cannot keep track. The memory of MATLAB is not such that it can add numbers like 10 to the negative 20 and 10 to the negative 24 together and get you something. It practically considered them 0 for arithmetic operations. Okay, so this epsilon can be something like that. Good. And continue with this epsilon instead. So what would you get if you do so? So what do you get here? It is going to be 2 times epsilon minus 2 times 0, so 2 epsilon, and then divided by epsilon, you will get a 2 here. Okay, so this is equal to 2 times epsilon minus 2 times 0, and then divided by what? By epsilon. Okay, so you will get 2 here. Now you look at the first column. Is there any change in the sign of the first column? No, because everything is what? Positive. So no sign change means what? Means the system is stable. Okay, and we can check it. All you need is to pass to MATLAB 1212. Right, so use the command roots of 1212, and if you see, the system is not unstable, but actually it is marginally stable. Okay, so we cannot say it's pure stable, it's marginally stable, but clearly it's not unstable because there is no change in the sign. Why is it marginally stable? Because 2 of the roots are pure imaginary. This one goes to 0, these 2 will keep oscillating. So if I now go back, I read from you, from the PowerPoint from you. So it says, if any element of the first column is 0, but the remaining terms are not, or there is no remaining term. In this case, This one was 0, but there was no remaining term. I added the 0 artificially myself. But sometimes the rows are bigger, so here there are some more elements and none of them is 0 except for this one. Okay? If that's the case, then you replace that 0 by a very small positive number called epsilon and you keep calculating. Now, it says if the sign of epsilon, if the sign of coefficient above epsilon is the same as the one below it, it means there are what? A pair of imaginary roots. If the signs are different, then there is a root with a positive real part. So in this case, the coefficient above it is 2, below it is 2. They have the same sign. So there are roots with what? Yes, pure imaginary. So because these two are both positive, it means what? There are pure imaginary roots. And when they are imaginary roots, means it's not pure stable, we call it what? We call it marginally stable. Okay, so you see, it's not unstable, but it's marginally stable. So this is one special scenario that can happen. But again, if the two numbers above and below it, one of them was positive, one was negative, then yes, there was definitely what? A change in the sign, and there was definitely a root with the positive real part, so the system became unstable. In this case, it's not. The other case you have, which is even worse than that, is all of the coefficients in a row become 0. It says if such a thing happens, then there are roots of equal magnitude lying radially opposite in the S-plane, which means what? Either two real roots, one of them positive, one of them negative, or two what? Conjugate imaginary roots. So two roots like -2 and +2, or two roots like what? 3j and -3j. In such case, if we want to continue, we form an auxiliary polynomial with the coefficients of the last row, means the last row before the row of all zeros, and what? By using the coefficient of the derivative of that in the next row. Okay? So we replace that row of zeros by the coefficients of what? The last row, we form an auxiliary one, we neglect that, and then what? We take derivative of those coefficients, and then we form the next row. So let's take a look at this interesting case and do it. So here is a fifth order polynomial. I start with s to the 5, s to the 4, 3, 2, 1, and 0. I start with 1, then 24, then -25, then 2, then 48, and then -50. Now let's calculate. So this is going to be 2 times 24, that's 48, minus 1 times 48, that's 48. So 48 minus 48, that's 0. 0 divided by 2, that's 0. Then I use the first row and the first column and third column. So 2 times -25, that's -50, minus 1 times -50. So minus 50 is plus 50. So negative 50 plus 50, so that's 0 also. Divided by 2, again, I get what? 0. So now if you look at this interesting row, it is all what? This guy is all zeros, right? And it's not like the one that only the first element was 0 and we considered it epsilon. So here you have more than 1 0 and you're not going to do it. This is epsilon, that is delta, this next one is whatever, and just say all of them are positive. No. In this case, we deal with it differently. So now, what do we do? As it says, we form an auxiliary polynomial using the coefficients of the last row. So the row right before the zeros is this row. And what kind of auxiliary polynomial does it give me? Well, if you look, this 2 was for s to the 4, so it is going to be 2s to the 4. The 48 was for s squared, so plus 4ds squared. And then the negative 50 was just constant. So this is going to be your auxiliary polynomial p of x. So do not say, well, this is 248 and negative 50, so my polynomial is 2s squared plus 48s minus 50. No, it's not. Because you're starting from s to the 4, and the next one is not s to the 3, the next one is s squared, because if you remember, we got these coefficients from here, here, and here. So whatever we got from the original polynomial, we use it over here, okay? So do not form something from scratch. You have to use the same terms from the original polynomial. So first, we take this, and then we take a derivative of this. So p prime of x is what? If we calculate first derivative with respect to s, it is going to be 8s cubed, and then plus 96s, and plus 0 constant. So we use the coefficients of this derivative in this row instead of all these zeros. So we come here, get rid of this, and we use these coefficients, 8 and what? 96. We use these guys in here instead. We replace that row of zeros. And now we continue. If you do it, it's going to be 8 times 48 minus 2 times 96 divided by 8. And I calculated that number. It is going to be 24. Then here I don't have a number, so I have to artificially add a 0. So it is going to be 8 times negative 50 minus 2 times 0 divided by 8. So it is going to be what? Negative 50. The next one is going to be 24 times 96 minus 8 times negative 50 divided by 24. Again, I calculated that number. It is 112.67, if I'm not mistaken. Yes. And here I don't have anything. I can again plug in 0, and the last one is 112.67 times negative 50 minus 24 times 0 divided by this, which is going to be what? Negative 50. Now I look at what? The first column. Do I see any sign change? Yes, I see 1 here. So there is what? There is 1 sign change. Therefore, there is 1 root with positive real part on the among the poles, and so the system is what? Unstable. and I can always go and check it. Okay, so if I pass these coefficients to the command roots in MATLAB, which I did already, look at them. So 4 of them have negative real parts, except for this guy. This one is positive 1, and that means your system is what? Unstable. By the way, this method says there are it is an indication of 2 real roots with different signs or 2 imaginary roots with opposite imaginary signs. So that's correct, because if you see here, I have negative 1 and what? Positive 1. So I have 2 real roots with what? Different signs of real part, and actually I have 2 imaginary, pure imaginary part with what? Opposite imaginary signs. I have all of them. But still, that 1 is enough to make my system what? Unstable. So this is how we use this very important method, and it is capable, as I said later, when we design controllers, it is capable of telling us how much of a parameter, because when we design controllers, the controllers have parameters, okay? Like a PID controller has 3 gains, PI and D gains. So we need to know what ranges of those parameters we can choose so that the system does not go unstable. How can we tell? This method can help us.